Hi, in this lecture, we will talk about shape functions and finite element discretization of the weak form that we derived last time. So if you go back to the weak form that we derived in the last lecture, if you look at this equation and keep in mind that our goal is to solve for u, which is the unknown in our PDE, to evaluate these integral equations, we need to have a priori assumption on the structure and form of u that lets us to easily evaluate these integrals, calculate them numerically, and then find u. So to do that, we need to assume u to be of a certain form. And in finite element, typically we either assume u to be linear or quadratic functions. Now, if you think about it that way, if I assume u to be a linear or quadratic function and then go ahead and evaluate these integral equations in my weak form, the issue there is that if I take my domain omega to be the entire domain of interest where I'm interested in solving my PDE, it's very likely that the linear or quadratic function is not sufficient to capture the complex solutions that we're typically after. So the idea in finite element is that what we're going to do is that we're still going to assume that the solution behaves linearly or quadratic form. However, we're not going to evaluate this integral over the entire domain, but what we're going to do is that we're going to discretize our domain into small elements, and over each element, then we can reasonably assume that the solution behaves linearly or in a quadratic fashion if you want to have more accuracy. So that's the idea behind discretization and finite element and shape functions. So if you take a 1D domain like this, you can divide it up into a bunch of elements. So if you zoom in into an element, we denote an element by superscript E, so omega E. And in 1D, you can see that this element has two nodes, node 1 on the left, node 2 on the right. And delta X is the size or the edge size of this one-dimensional element. Now, what I'm going to do is that I'm going to assume my solution so I can solve u. I assume it behaves linearly over each element. And all I'm going to do is I'm going to find what is the best linear function across this element. So you can imagine if this is a true solution, u that satisfies the PDE, what I'm really after is that I'm after dividing my domain into these small elements and finding the best linear, piecewise linear function that's as close as possible to the true solution, right? So that is the goal. And we do that through these linear interpolation functions and also known as the shape functions. So in this case, in this one-dimensional example, I have two of these shape functions, one associated with each node. So on node 1, I have the shape function n1, which is defined as 1 minus x over delta x. And over node 2, I have a shape function n2 defined as x over delta x. Now, the shape functions associated with each node are such that their value is equal to 1 at that node, and the shape function is 0 at the other nodes. So if you look at n1e, if you plug in x equals 0, so this is my x coordinate. If you plug in x equals 0 here, you can see that this is indeed equal to 1 at its respective node, 1. And if you put x equals delta x, so the location of the other node, this becomes 0 as desired. And same thing for n2. If you put x equals delta x, this becomes, which is the location of node 2, this becomes 1. And if you put x equals 1, the location of, or rather x equals 0, the location of the other node, this becomes 0. So then, with this property in mind, I can write my solution over this element omega e, so not globally, but rather locally across this element omega e, I can write as n1, which is a shape function I know. Okay, so I know exactly these shape functions, what they are. They're not unknown. So it's n1 as a function of x times u1 of e. So this is u1. E is the solution at node 1, which is what I need to find. Plus N2, which again, I know what it is, times U2 of E, or solution at node 2 for element E. So this is my hypothesis for my solution over each element. I assume that the solution over each element is an optimal linear function that I define as such using these interpolation functions. And you can think about anywhere in between. If you're anywhere in between point 1 and 2, your solution is kind of like a linear interpolation of your nodal values. Now, if you look at this U sub h, and I use the subscript h to motivate that now I'm in a discretized space. So h here kind of represents the mesh h size. So when I write U sub h, I mean, I'm talking about the discretized solution, but if I just write in U, I mean the actual continuous solution. Now, so if I take my discretized solution, so this equation, I plug in x equals delta x, which is location of node 2, n1 becomes 0 at that x equals delta x. So this goes away. N2 is 1, so I just get U2. So, okay, so that's exactly what I wanted. I wanted this to be such that at x equals delta x is U2, the solution at 2. And similarly, if you put x equals 0, you can see that this is equal to U1 as you like. Okay, so now that's the details for the simplest case. It gets a little bit more involved once you go to 2D and 3D elements, but the concept is the same. And really, just from big picture perspective, the concept here is that over each element, we're approximating the solution. So that's U sub h to denote a discretized solution as a linear function. So in 1D, this is something like ax plus b, where we need to find the exact form of that linear function such that we're getting the best solution to the PD. Okay? Now, if we wanted to go to second order spatial discretization or quadratic shape function, quadratic interpolation, then we will need to expand this equation to this form. So now we're going to have 3 shape functions as sketched here. And you have kind of like a middle node, if you like, a mid node, node 2. And you can see that the same properties hold. So for example, for N2, it's equal to 1 at midpoint 2, but it's 0 elsewhere. And same thing for the other ones. They're 0 at the other nodes, but they're equal to 1 at their own respective node. So then we can, with that property, we can write the total solution, the interpolated solution at any point across inside the element as this equation. Now, if you want to look at the big picture, again, really all we're doing with quadratic shape functions is that we're finding the best possible quadratic function that satisfies the equation, the governing equation. So that's nothing but an ax squared plus bx plus c over each element. Now, in 2D, okay, so if you're dealing with a 2D mesh and you're using triangular elements, so your element now has 3 nodes. So from a big picture point of view, you can think of the solution UH across each omega E, each element being approximated by a linear function if you're using linear interpolation functions. So that would be something like AX plus BY plus C. So you really have how many unknowns? 1 through 2, 3, A, B, and C. Which you guys think about, you have 3 nodes, right? And then if you're doing quadratic shape functions, you're looking at the most complete quadratic form in this 2D space. So that's given by this function. This is the most general quadratic polynomial you can assume over a 2D space. And if you look at the coefficients A, B, C, D, E, F, you have 6 unknowns now. Okay? So now, more details on how exactly the shape functions for triangular elements are, defined. You have to look at more introductory finite element references. We're not going to go over that in this course because all of this is taken care by FEniCS. And as I mentioned, this course is motivated by FEniCS. So if you're interested in learning more about details of these shape functions, particularly in 2D or 3D, I encourage you to check out one of the introductory finite element references like the book by Reddy, which is what I recommended in the first lecture. Okay, so now let's look at the discretization of our specific Poisson or Laplace equation. So this is a weak form we derived last time. If you look at, we can define some function spaces now. The space U is a space of admissible trial functions. So this U's, which is the unknown we're solving, we also call it the trial function in finite element. So the space of all possible solutions that are allowed are U, and W is a space of allowable or admissible test functions or are also weight functions. And what are these spaces exactly? Well, U is the space belongs to H1 Sobolev space. So if you remember H1, this is the space of all functions that are L2. So the function is square integrable, but also its first derivative is square integrable. And the reason we restrict ourselves to this space is because if you look at the weak form, we have first derivatives multiplied. So we are looking at an H1 space. And we also have a constraint that U is equal to U bar on the Dirichlet boundary. So we're enforcing the Dirichlet boundary in the space of admissible solutions. We're not allowing U to violate the Dirichlet boundary condition on the Dirichlet boundary. And we have the same space for the test functions W. The only difference is that, as we mentioned last time, if you think about these test functions as your variations, their variations are not allowed on the Dirichlet boundary because we exactly know the solution. So W is equal to 0 on the Dirichlet boundary. So now, after we discretize our mesh, so something like this, these U and W spaces are now become a finite dimensional space because now we're in a discretized space. So we use this subscript H to denote that we're talking about the discretized version, and H represents the mesh H size scale. So now we can write our discretized solution UH as the sum of multiplication between the shape functions and the nodal values, what we just talked about. And what we do is that we typically distinguish between the nodes that are not part of the Dirichlet boundary, and then we separate out the part that belongs to the Dirichlet boundary, and we deal with that separately. So we will talk more about this later and how we exactly do that. And there are different ways to do that. For the weight function, we have, again, some other shape functions, which we denote with M times some W's, A's. So in the solution case, in the trial function U sub A's, these are the solutions at node A. Okay, so these shape functions N are known, right? They're equal to 1 at the nodal value. So your total solution is UA, which is the solution at node A. Now, for the weight function, W sub A is arbitrary because the test function was an arbitrary function, really. We took the PDE and multiplied both sides by W. We could multiply both sides by anything we want, really, as long as it's smooth enough and we can do the mathematical operations we want. So really, the easiest way is just take WA to be uniformly equal to 1. Okay, so this will just go away. Now, in Galerkin finite element, we also do another simplification where we assume these shape functions between the trial solutions and also the test or weight functions are the same. So this N and M are the same. So now, if you take these equations and plug it into the weak form, this is the equation you will arrive. So we can come at this equation. So you can see that the equation is very similar to the weak form we had, but now really U and W are kind of replaced by these sums over these shape functions. Okay, and here where you only have sum over shape functions, you don't have any unknown coefficient because remember this is the weight function being multiplied by the Newman boundary, and the weight functions nodal value is really just set to 1. Okay, so this becomes our weak form. And what we can do is that these integrals, we're not going to evaluate it over the entire domain, really, because over the entire domain, it's silly to assume the solution to be linear or quadratic even. So what we do is instead is that we evaluate these integrals one by one across all elements. So then we can denote this element stiffness matrix, K superscript E, as the first term corresponding to the diffusion Laplacian operator in our PDE. Okay, so this is evaluated on the local element. So it's just a tiny element uh, that's part of our entire domain. And the same thing with the right-hand side, F, which constitutes the source term and the Newman boundary condition. So what we do is that we evaluate these across each element. So that's what the superscript E denotes. So these are integrals over each element. And what we do is that we loop over all the elements in our domain. We calculate this, this matrix and this vector really, which are like a tiny matrix and vector because they're just corresponding to less degrees of freedom. We calculate them and then we assemble them to form this big stiffness matrix K and a big forcing vector, right-hand side vector F. Okay, so after we do this assembly, and the way we do that assembly is that, for each element, we know what's its coordinates connectivity, what are its IDs the IDs of the coordinate with respect to the global mesh. We know that. So when we do the assembly, we know where to place them, and also add on top of what's already there, these local tiny K matrices that we compute into the very big picture stiffness matrix K. So ultimately, this is what becomes. We get the linear matrix, a matrix K times a vector of unknowns, which contain the solution, the unknown solution at each node of the mesh, equal to the forcing term, the right-hand side, which is known, F1, F2, and all the way to the last node of the mesh. And this matrix K, which comes from these integrals, is also unknown because the material property K is unknown. And also these shape functions, we assume them a priori, right? Their form we assume. And the unknown part is dragged into this unknown vector. So now there's a lot of detail on how you do this assembly, and how do you actually form these matrices. But again, we're not going to be talking about those in this class because FEniCS, takes care of the assembly of these matrices for you. And if you're interested to learn more about the details process that goes behind these operations, again, I refer you to an introductory finite element textbook like the book by Red.